Now that we have figured out how to exchange data between the host and device, it's time to send some useful information. Like always, the host would request this data first with the setup packet, and the request will always have the same structure. The answer at this stage will always be some kind of descriptor. We'll take a look at the request structure first. The requests have 5 values. Some of them are 8 bits long, some are 16 bits. Overall, the request has 8 bytes of data. Some values are not important for now, but some are. The first field, the request type, indicates among others whether it is an in or out request. Depending on that, the device will have to send or receive data. The second field contains actual request, whether it is to describe the device or to assign an address, etc. The following 2 fields may be used differently for every request, and the last field, the length, is the length of the data that's about to be transmitted. The first thing the host requests from the device is to describe itself. The device is supposed to tell its manufacturer, serial number, protocol it can communicate, etc. No worries, none of that matters for now, although we have some fields that need to be considered. Let's go through the descriptor field by field. Length is the length of the descriptor. Device descriptor is always 18 bytes long, so this field will always have to be 18 or 12 in hex. Descriptor type is the identifier of the descriptor. For device descriptor, it's 1. Next goes the USB version the device supports, a 2-byte field. If we use USB 2.0, these bytes should be 2 and 0. Also, USB packets are a little endian, and its 2-byte fields should be inversed. So for USB 2.0, value should be 0 and 2. Device class, subclass, and protocol. These values describe what driver can communicate with the device. For example, the class may be a mouse or a microphone. And if the host have a driver for USB microphone, it may use this driver for the device. Here I leave these values at 0, meaning that we'll set them later. Maximum packet size. Okay, this one is important. Intuitively, it's how many bytes the device can transmit at one go. It can be 8, 16, 32, or 64. If the device is unable to send its message in one packet, some complicated things happen, so we'll set this value at maximum 64 byte or 40 in hex, and try our best not to send more than 64 bytes at one go. ID vendor and ID product are the identifiers for the device and manufacturer. They are important if you plan to distribute your device. For this first test, these values can be pretty much anything. Device version is self-explanatory and is not important for now. Next follows string descriptors, which are also not mandatory, and value 0 means that they are not used. The last value is the number of configurations that the device have. We'll only be using one configuration. After the host has received the device descriptor, it will require something called configuration descriptor. This one tells how many interfaces the device have, more on them later, and how much power the device uses. The first 2 fields, as all descriptor, contain its length, which is always 9 bytes, and ID, which is 2 for the configuration descriptor. Next follows total length. I will explain it after a couple of slides. And then goes number of interfaces. We'll only use 1. Then goes ID of the configuration, which may be any value, and string descriptor, 0 meaning it's not used. Then there are attributes, which are not really important for this first test, and maximum power the device can use, in 100th of watt. Here value 19 hex or 25 in decimal, meaning that the device can use 0.25 watts of power from the USB device. Next descriptor is the interface descriptor. It tells what the device can do and what protocol it uses, basically so that the operating system can decide what driver to use for this device. Let's take a look at its values. Length is always 9 bytes, descriptor type is always 4, interface number and alternate setting are not important now, we leave them 0. We won't be using any endpoints except the mandatory endpoint 0, so number of endpoints can be set to 0. These values define what driver can run the device, and value of FF hex means it's fully custom device and only a fully custom driver must be used. We will write this driver later. The last field is related to a string descriptor. We'll leave it 0 as it's not used. Fetching the configuration descriptor is tricky because its length may vary. The descriptor also contains interface and endpoint descriptors, so its full length is unknown. The host systems act differently to fetch the descriptor. Linux system would request the first 9 bytes of the configuration. It contains a field called total length, which is the total length of the configuration descriptor with all its interfaces and endpoints. Linux then reads this field and requests for the full configuration. Windows system would request for much more data than the descriptor may have, say 255 bytes, and see how large is the message that arrives. So overall, there are 9 operations we have to go through before the device can communicate with its driver. First, reset. Second, send the device descriptor. Third, set address request. The host tells the device its address, which is a single 1-byte number. The device needs to remember this number. Fourth and fifth, reset again and send the device descriptor again. Sixth, something called device qualifier descriptor, which we can ignore for now. Then 2 stages of the configuration descriptor, and finally the set configuration request, for which we just need to respond with an empty packet to signal that the request was processed. Now, before we proceed to the coding section, there is a couple of things to keep in mind. When I get to the code, I will split the setup request into its values, and I will handle the value part as a pair of 8-bit values instead of a single 16-bit value. This is valid because the request may contain different data in the most significant and least significant bytes. Another thing to keep in mind is the indices of the array when it has been cast to 8-bit or 16-bit values. Here on the slide, I have the same array being cast to 8 and 16-bit values. To access the bytes 6 and 7 of the data, I have to use indices 6 and 7 if this is an array of 8-bit values, but index 3 if the array has been cast to 16-bit values. One last thing, Linux has a tool called kernel log. All the modules can write to it, and it contains information about the devices being connected to it. I will use this tool to check out whether the machine has detected my device, what address has been assigned to it, etc. You can see a sample from the log on the screen. Here it notifies that the machine has detected a USB device and assigned it number 6. That is all theory for now. Let us switch to the IDE. The next thing to do is to give names to the parts of the request. We want to avoid expressions like if the request type is AT. We want to say if the request is standard and the request is for a descriptor, and the descriptor is the device descriptor, then send the device descriptor. So there are multiple types of descriptors, followed by requests like set configuration or set address, which I will add later. Next, I organize the setup packet. First byte is the request type. Second is the request itself, followed by 2 data bytes, and the requested length, which is bytes 7 and 8. But if I cast the array to uint16, it's gonna sit in position 3. So let's handle the requests. The response to a standard request, get descriptor, specifically device descriptor, will be this line I wrote before. On the other hand, if the request was to set address, whose index I'm adding now, we call the HEL setAddress function. The data1 field will hold the address we've been assigned, and we have to respond with an empty message to signal that the request was processed successfully. A little print also wouldn't harm. Let's give it a build and see how it performs. Okay, we do see that address 9 have been assigned, and the host sends us different requests, meaning that the process has gone forward. Now we're going to check what it looks like from the host perspective. I reinsert the device and see the request to it before it's been assigned an address. Change the filter according to what I saw in the console, and there is nothing in there. I check the kernel log to find out what Linux thinks the device address is. It looks like it's been around 65. Still not sure why my device was printing 9, there may have been a mistake at my side. Anyway, back to the log. It says the request have been returned with a no entity error. In contrast, for the device descriptor request, we see a success status. Okay, looks like the host wants a configuration descriptor, so let's send it the configuration descriptor. Back to the device code. I will add the descriptor right below the previous one for the device. The first 2 fields are much like all the other descriptors, a length and an index. Then follows the total length because this descriptor will be sent in combination with several other descriptors. Next follows some fields we should not worry about for now. Leave the number of configurations and interfaces as 1. Some power-related information I leave kind of default. Next goes the interface descriptor that starts as always with the length and an index. Its number and alternate setting can be left at 0. I won't be using any endpoints beside the default one. Next follows some fields that describe the functions that the device can do. It allows the host to assign a driver to the device. FF and hex means that only custom driver can handle it. The last one is an index of one more string, 0 meaning it's not used. Now we have to set the total length of the descriptor at some point. Here I do it in the reset callback. It can be done anywhere before the descriptor is sent to the host. The total length is 3rd and 4th byte, but since I cast the array to 16-bit values, the total length sits at position 1. Now I add actual response. If the request is for the configuration descriptor, then the device sends it. Fixing little typo here. The following request after the configuration has been sent will be the one called setConfiguration. It would be useful if we had multiple configurations. Here I am adding its ID, and you may have noticed that this ID was already present. I probably was tired when recording. I will fix it in a moment. Also, the configuration descriptor here should be 2. I will also be fixing it. Now we need to send an empty packet in response to this request to signal we've received it. The host sends the device the configuration ID to activate. I will print it out though we only have one configuration. Okay, my compiler says I missed a curly bracket here. Starting a debug with this code. Here I realize that error with the descriptor ID, giving it a fix. Oh, I also found the duplicate define, giving it one more build after the fixes. Now this code does work, so let's take a look at the host perspective. I restart the USB capture. The device has been unplugged several times and its address has changed. The kernel log somehow did not update. The error message is still no entity. I try reinserting the device, check its address again. That's better, looks like I had to just give it a little bit of time to update. Now, when the set configuration response was successful, the enumeration process is completed. Here we see 2 configuration descriptor requests, one for the first 9 bytes to figure out the total length of the configuration. The second was for the whole configuration. And just like that, we got ourselves a USB device.